In this lesson, we're going to solve higher order inequalities. That is, nonlinear inequalities. Let's start with a linear inequality and what we know about them. You can solve a linear inequality the same way that you solve a linear equation. So we can just add to both sides, subtract from both sides, etc. So let's subtract x from both sides. That'll give us 5 minus 3x is less than or equal to negative 4. Now we can subtract off 5, and that's going to give us negative 3x is less than or equal to 9. And dividing through by negative 3, that changes the direction of the inequality, so we get x is greater than or equal to 3 is the solution. Oh, and I forgot, we're supposed to write this in interval notation. So in interval notation, that would be the interval starting at 3 and heading toward positive infinity. And it includes 3, so we use a square bracket on that. There's our interval notation answer. Now we're going to solve the same inequality graphically. In order to solve graphically, we'll need to graph each side of the inequality. So we're going to graph first y is equal to 5 minus 2x. That's just going to be a straight line with a y-intercept of 5 and a slope of negative 2. So we can graph that. And then I'll use a different color for the other line. We're going to graph the other side of the inequality, y is equal to x minus 4. So that's going to be a line with a y-intercept of negative 4 and a slope of 1. And so now here's what I want you to notice about these. This kind of looks like how we solve a system of equations. And when we solve a system of equations, we're looking for that point where the two graphs intersect. I want you to notice something about where those two graphs intersect. They intersect at x equals 3. Now, if you remember, 3 was a value from our original solution, or the interval. We had x greater than or equal to 3. And what I want you to realize is that's where the y values, or the two sides of the inequality, are equal to one another. Now we're looking for where the, if we take our inequality, we're looking for where 5 minus 2x is less than or equal to x minus 4. So we are looking for where that blue graph is lower than the red graph. So what you're going to notice is that if we head to the right of 3 and just look at this portion of the graph right here, you'll notice that the blue graph sits below the red graph. And so what interval is that? That's the interval starting at 3 on the left and heading toward positive infinity. So let's remember something about absolute value inequalities. I know you have lots of good memories of those from Algebra 2. Let's take a look at an algebraic solution for the absolute value of x minus 2 is greater than 3. What you have to remember about this one is a step where you take x minus 2 and you say it's either less than negative 3 or x minus 2 is greater than positive 3. And then solve, and that's going to give us x is less than negative 1 or x is greater than 5. And if we were to graph this on a number line, it's going to give us open circles on negative 1 and 5 and shading to the left and to the right. Interval notation would be the interval from negative infinity to negative 1, union interval from 5 to infinity. So there's our solution algebraically. I think the graphical solution might make a little bit more sense to you. So let's let our blue graph here be y equals the absolute value of x minus 2. And let's let our red graph be y is equal to the other side of the inequality, which is 3. Now let's concentrate on our blue graph here first. So we'll move over to the grid. Y equals the absolute value of x minus 2. If you replace x with 2, you get 0, so that's the point 2 comma 0. And then if we replace x with 3, we get 1, etc. And if we replace x with 1, we get 1 minus 2 is negative 1, taking the absolute value, that's positive 1. So you can generate your whole list of y values. And that one should look familiar to you from a transformation perspective. It's just that V-shaped absolute value graph, but it's moved right to. All right, now let's concentrate on our red graph. Our red graph is y equals 3, which is a horizontal line. And now let's think about what we're looking for graphically from this. We are looking for where our, we take our original inequality. The original inequality states that the absolute value of x minus 2, which is our blue graph, is greater than 3, which is our red graph. So we have blue is and greater than means for y values, that means higher than the red graph. Now this one was not or equal, and you may remember that when we have the two graphs intersecting each other, that's where the y values are equal to one another. So we can think of these two values as not being included. Those are the values of x at which the graph of the blue graph is has an equal y value to the red graph's y value. Now we want to know where the blue is higher. So the blue graph is higher on the left side and on the right side. So that gives us that same interval, negative infinity to negative 1 and 5 to infinity in terms of just the x values. Just remember, we've introduced the variable y, but we're looking for a solution that gives us intervals of x values. Now, the next one, I promise you, you do not want to solve it algebraically, so we're actually just going to skip the algebraic method on this one. You can try to solve it algebraically, but it's going to be wrong. It's a much more difficult algebraic solution than what you might think. So you cannot solve a quadratic inequality the same way that you solve a quadratic equation. So let's just solve this one graphically. And so we're going to graph y is equal to x squared plus 2x minus 3. And this is one where if we want to graph this, we're probably just going to have to complete the square. So I'm setting that 3 to live with the y. And then we're going to introduce our plus blank. And take half of the 2, that's 1, and square it, that's 1. So now we have y plus 4 is equal to x plus 1 squared, or y is equal to x plus 1 squared minus 4. So our vertex is at negative 1 comma negative 4. And this one has an a equal to 1, so this one's actually pretty easy to graph in terms of just going to the right and to the left. If you go over 1 from the vertex, you're going up 1 squared. If you go over 2 from the vertex, you're going up 2 squared. And if you go over 3 from the vertex, you're going up 3 squared, or 9, which puts us at a y value of 5. So there's a nice graph of that parabola. And our red graph is going to be the other side of the inequality, which is just y equals 0. Now y equals 0 is just the x-axis. So now let's take a look at what our inequality was stating. Our inequality was saying x squared plus 2x minus 3, which is the blue graph, is less than or equal to 0, which is the red graph. And so we are looking for where the blue is lower than or intersecting the red graph. Well, we can certainly take a look at where the red and the blue are equal, and those are going to be at x equals -3 and x equals 1. And then where is the blue lower? The blue is lower in between those two x values. So the solution for this one is the interval starting on the left at x equals -1 and at x equals -3 and ending on the right at +1. And so this is actually going to be easier than solving algebraically. Some observations, things that you will need to be aware of. Linear inequalities, easy to solve algebraically. And by algebraically, I mean by adding, subtracting, moving things around in the inequality. Absolute values, easier to solve graphically. And quadratic inequalities, the graphical method was not too bad, wasn't super easy either. So we're actually going to prefer another method on these. They're going to be easier to solve with a number line. We're going to learn how to utilize the number line in just a moment. Nonlinear inequalities may not be solved the same way that you solve linear inequalities. The easier method uses a number line to analyze when the expressions that we're dealing with are positive, negative, or 0. So here's how we're going to analyze the sign of a polynomial using a number line. We express the polynomial in factored form, find the zeros of the polynomial, and mark them below your number line. So let's do that for example 2. So we're going to find the zeros, and our zeros are x equals 6, because that would make this the expression equal to 0 and x equal to -1. They're just basically what makes each of the factors equal to 0. So I'm going to mark those off on my number line, put the x values below the number line. Above the number line, we're going to write what each of those values does to the value of the expression. Well, we just said it. Each of those values makes the expression 0. On the top of the number line, we're going to indicate what the value of the expression is. Now, this is the only quantitative value that we're going to put on the number line. The rest of the values we're just going to qualitatively look at and see if they are positive or negative. So you notice that we divided our number line up into 3 intervals. So let's take a look at the interval that falls on the left side of -1. That would be the interval from -infinity to -1. And we need to pick a test value on that interval. So I'm going to pick x equals -2. Now we're going to take that expression, the polynomial, and replace the x's with -2. So x minus 6 times x plus 1 squared. And I picked an x value of -2 to plug in. So now what we're going to do is not actually necessarily get the value, but just think about whether this value is a positive number or negative number. And we're going to use the rules of multiplication for determining this. So what I can see is that -2 minus 6 will be a negative number. -2 plus 1 is a negative number, but then we square it, and it's going to be positive. So overall, that gives us a negative number. So above the number line, I'm going to indicate that for that interval, the value of the polynomial will be negative. Now, it doesn't matter what test value on the interval you pick, it's going to give you the same result Not the same numerical result, but the same qualitative result, negative. All right, now the next interval that we can consider is the interval in between -1 and +6. I'm going to pick a test value on that interval. X equals 0 is a nice one to pick. Usually easy to do computations with x equals 0. And then we'll plug it in. And so if we replace the x's in the expression with 0, 0 minus 6 is a negative number. 0 plus 1 is 1. Squared will be a positive number. So that means the result is negative as well. And now we have one last interval to test. That's the interval from 6 to infinity. And let's pick 7, for instance. Again, it doesn't matter what value you pick. And let's replace the x's with 7. And so for this interval, 7 minus 6 is a positive number. 7 plus 1 is 8. Squared is a positive number. So overall, the polynomial is positive times positive, which is positive. And that is our number line for the polynomial. Now I'm writing out all of these computations. Once we get a little bit further along, you will not necessarily write all of these out. Some of them you'll do in your head, and we'll also find a way to make it shorter where you don't have to do as many test values. All right, let's check out the next one. More complicated expression. This one is in factored form, and so we have the zeros, and the zeros are going to be 0, 1, and 5. One thing that I need to tell you is make sure that you put these values in order on the number line. The spacing doesn't matter though. So I know that 1 and 5 are farther away from each other than 0 and 1, but it doesn't matter as long as we get them in the correct order. So those guys make the value of the polynomial 0. Now we have 4 intervals to test. So we're going to start here on the left. On the left of 0, let's pick a value of -1. And then replace the x's with -1. So we have -1 cubed. That's going to be a negative number. -1 minus 1 is -2, but then we square it, so that's a positive number. And then -1 minus 5 is a negative number. So I'm just going to note this factor was negative, this factor was negative, the one in the middle was positive. So we have a negative times a positive times a negative. Whenever we have an even number of negatives that we're multiplying together, the result is going to be positive. So I'll put a little plus over the number line for that interval. Now the next interval is between 0 and 1. So let's pick a half. Now don't worry, if you have a fractional value, it's not really going to matter that you actually find the values. It's just qualitatively looking at whether the polynomial is negative or positive. So we have a half cubed times a half minus 1 squared times 1 minus 5. So a half cubed is a positive number, so I'm not going to mark off that one. A half minus 1 is negative, but when we square it, it's positive. And 1 minus 5 is negative, so I'll mark off that one. We have just one negative factor, so that means overall the value of the polynomial there is negative. Mark that off on your number line. And then let's pick the interval from 1 to 5. I'm going to choose x equals 2. You can choose 3, 4 if you want to. And let's replace x with 2. So we have 2 cubed, that's positive. 2 minus 1 squared, that's positive. 2 minus 1, 2 minus 5 is negative. So we have only one negative factor. So overall, that's negative. Mark that off on my number line. And then finally, the interval starting at 5, heading toward infinity. Let's pick x equals 6. And replace x with that value. 6, make sure to bring down those exponents. I forgot that one on the 6 cubed. All right, so 6 cubed is a positive number. 6 minus 1 squared is a positive number. 6 minus 5 is positive. We have all positive factors. So overall, the polynomial is positive. Mark that off on the number line. And there's our answer. Now, you might say, well, what are we accomplishing? We're actually going to utilize the skill of the number line to solve an inequality in a moment. Last one is not in factored form, so we're going to need to do a little bit of work. And we're just going to write this one as x plus 1 squared. That means that we only have one 0. At -1, the polynomial is 0. So let's pick some intervals here. The interval from -infinity to -1. And let's pick a value of -2. So -2 plus 1 squared is a negative number squared, which is a positive. And from -1 to infinity, we can pick x equals 0. And that also gives us a positive number. So this polynomial is either 0 or positive. Now let's talk about a vocabulary term. This is called multiplicity. Multiplicity of a factor corresponds to the exponent in prime factorization. So for instance, 40 is 2 cubed times 5. So the 2 is a factor of multiplicity 3, and 5 is a factor of multiplicity 1. Just talking about the exponent in prime factorization. So now let's make some observations. We're going to look for some factors here of multiplicity 1. So x equals 6 is the 0 that we got from that multiplicity 1 factor in 2a. And I want you to look at what happens at 6. At 6 on the number line, we have a change from negative to positive. Negative on the left, positive on the right. Let me find another multiplicity 1. In b, we have a multiplicity 1, x minus 5. That gave us a 0 of 5. And if you look at 5 on the number line, the polynomial is negative on the left, positive on the right. And that's it for our multiplicity 1 factors. Now let's look at multiplicity 2. Multiplicity 2 factors. Here's x plus 1 squared. That one gave us -1. Take a look at -1 on the number line. The sign of the polynomial is the same on both sides, negative on both sides. In b, x minus 1 squared. That gave us x equals 1 as a 0, negative on both sides. And last one, x plus 1 squared. That gave us -1. Look at the polynomial, positive on both sides. So to kind of put it together, when we have odd multiplicity factors, those would be like 1 and 3. I can't read that. So 1 and 3, or 5 even, the sign of the polynomial changes. It'll be different on the left side of the number line than it is on the right. At zeros from factors of even multiplicity, the sign of the polynomial doesn't change. Same sign on the left as it is on the right of that 0. So if we want to solve a nonlinear inequality by factoring in number line analysis, we are going to set this up where we move all the terms to one side of the inequality, making the other side 0, factor and make a number line that indicates the sign, and then if the polynomial is supposed to be greater than 0, that's just going to mean positive. And then if the polynomial is less than 0, that means the polynomial is negative. And we're going to use multiplicities to cut down our process here to make it a little bit shorter. All right, so let's check out this first inequality. Take a look at this polynomial, x minus 1 squared times x plus 3. And so that's going to give us zeros on the number line of -3 and 1. At those values, the polynomial is 0. Now let's pick one test, and so this is where we're going to shorten it a little bit. We're just going to pick one test value. I find it easiest to pick a test value that's on the right side of the number line. So I'm going to pick one that's on that very right interval, bigger than 1. So I'm just going to pick x equals 2. At x equals 2, we have 2 minus 1 squared times 2 plus 3. And so that's going to be 2 minus 1 squared is a positive number, 2 plus 3 is a positive number. Multiply those together, we get positive. Now from here, we're going to use multiplicities. So we are looking at crossing over x equals 1. When we cross over x equals 1, let's look at that factor. That's multiplicity 2. That means the sign does not change. Now, when we cross over x equals -3, the -3 came from that factor. That factor's multiplicity 1. That's an odd number, so the sign of the polynomial does change. All right, now let's take a look at the inequality. The inequality said that the polynomial is less than or equal to 0. What kind of numbers are less than or equal to 0? 0 or negative. So now let's mark off on our number line where that polynomial is 0 or negative. So I'm just going to grab my highlighter and do this on the number line. Here's where the polynomial is 0. Here's where the polynomial is negative. So now I'm just going to copy that interval down off of the number line for our final solution, and that'll be the interval from starting at -infinity on the left to -3 on the right, inclusive, because that's where the polynomial is equal to 0, union, and then we have this weird interval that only contains one number, contains the number 1, and so you can write your interval that way, where you just use square brackets, including that number, and you just don't have a second number in the interval. All right, let's take a look at B. For B, we have to do some moving around of some things. So we've got to bring the 11x over to the left side of the inequality, and then we're going to factor. That's x minus 3 times x minus 8. And so now we have zeros of 3 and 8. So I'm going to mark those off on the number line, indicate that the polynomial is 0 at those values. Now pick a number that's on the right side of the number line. You don't have to do that, but that's probably the easiest. So what if we pick 9? If x is 9, 9 minus 3 is going to be positive. 9 minus 8 is going to be positive. Positive times positive is positive. Now what you'll notice about the factors there is they're both multiplicity 1. So at each of these zeros, the sign will change. Odd multiplicities, sign changes. Now let's take a look at the inequality. The inequality says the polynomial is greater than or equal to 0. So that means that it is positive or 0. So I'm going to take my highlighter and mark off where the polynomial is 0 or positive. and those would be on those intervals. Copy that down off of the number line. That's the interval from negative infinity to 3, inclusive, union 8 to infinity, inclusive. All right, one last example before you try this on your own. 2x squared less than x cubed. Suggestion, I would, when I move things around here, I would bring everything to the side of the inequality where you have the highest degree term as a positive coefficient. So then I'm going to just turn the inequality around and rewrite it as x cubed minus 2x squared is greater than or equal to 0. Factor out your x squared. So your number line has zeros of 0 and 2. Each of those x values makes the y value 0. And now let's pick a test value on the right side, maybe 3. 3 makes x squared positive. 3 minus 2 is positive. So the value of the polynomial is positive. 2 comes from the x minus 2, and that's raised to the first power, so there's a sign change because odd multiplicity. And then 0 comes from the x squared, and the x squared, since it's raised to the second power, is an even multiplicity, so we have this where the sign does not change. All right, let's read the inequality. The inequality says the polynomial is greater than or equal to 0. That means it's positive or 0. So I'm going to mark off on the number line using my highlighter where the polynomial is 0 or positive. Now copy that interval down. That would be what we call a degenerate interval that only contains one number, 0, union the interval from 2 to infinity. All right, your turn to try one. Try A below on your own. All right, here's the solution for this one. Notice that you have a multiplicity 2 factor. That's important to take into account when you're making your number line. Also notice that you can't say the interval all the way from 0 to infinity because 3 is an excluded value. We have an open circle there since we weren't doing an or equal to 0. All right, try B now. All right, here's the solution to this one. This one was already in factored form, so it made it a little bit easier. And there's lots of intervals to test, so using multiplicities is the best way to go on this one. Well, that's it for the lesson.